These are the stars that got kicked out of their own galaxy, and they are still out there right now, drifting through the empty space between the Milky Way and Andromeda, with nothing around them for millions of light years. This video covers what astronomers have actually confirmed about the space between galaxies, the individual rogue stars found wandering through it, the strange galaxies that live inside the emptiest voids in the universe, the decades of survey work that first revealed this whole structure, and what the physics of an expanding cosmos says about isolation on a scale most people never have a reason to picture. If you're new here, stick around, because this is one of those topics that sounds like science fiction and turns out to be sitting in peer-reviewed journals with names and dates attached. Like this video, subscribe if you want more of this kind of deep, calm, factual dive into space, and drop a comment telling me where you're watching from and what you're doing right now, because I genuinely love seeing who's out there listening to this stuff at 2 in the morning or on a long drive somewhere. Now let's get into it. Start with the number that breaks most people's sense of scale before we even get to the strange part. A megaparsec, which is the unit astronomers use for these distances, equals about 3.26 million light-years. Neighboring galaxies, meaning ones considered close to each other on a cosmic map, can still sit a full megaparsec or more apart, and the gaps between entire clusters of galaxies can stretch for hundreds of megaparsecs. Translate that into light-years, and you're talking about distances so large that light itself, the fastest thing in existence, would need hundreds of millions of years just to cross the gap one way. Here's the part that surprises people first. That space isn't a featureless black nothing. It has structure, and the structure looks like a web, which is actually the term cosmologists use for it, the cosmic web. Dense knots packed with galaxy clusters sit where the strands of that web intersect, connected by long filaments of gas and dark matter that stretch for hundreds of millions of light years at a time. Between those filaments are flatter regions called sheets, and bordering all of it are enormous, nearly empty stretches called cosmic voids. Dark matter is thought to be the scaffolding underneath the whole structure. The current understanding is that dark matter began clumping together first, in the early universe, shortly after the Big Bang, and its gravity then pulled ordinary matter into roughly the same shape, which is why, wherever astronomers find a massive cluster of galaxies, they also find a matching concentration of dark matter sitting right there with it. Durham University astrophysicist Richard Massey put it simply when he said that dark matter and regular matter grew up together, occupying the same places from the very beginning. It's worth pausing here to explain how anyone became confident dark matter exists at all, since the whole cosmic web picture leans on it so heavily, and the discovery story stretches back much further than most people realize. The first hint came in 1933, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a collection of more than 1,000 galaxies, roughly 100 megaparsecs away. Zwicky measured how fast individual galaxies inside the cluster were moving relative to one another, then used a piece of physics called the virial theorem to work out how much total mass the cluster would need in order for gravity to hold all of that motion together without the whole thing flying apart. Then he separately estimated the cluster's mass by simply adding up the light coming from all its visible galaxies. The two numbers didn't come close to matching. The galaxies were moving so fast that based on the visible matter alone, the cluster should have torn itself apart long ago. Zwicky concluded there had to be some other kind of matter present, invisible, non-luminous, but still exerting plenty of gravity, and he gave it a name that's stuck ever since: Dunkle Materie, German for dark matter. At the time, most astronomers treated it as a strange oddity rather than a serious discovery, and Zwicky's own guess about what the missing material actually was, cold dim stars, scattered solid debris, ordinary gas, turned out to be wrong. But the core observation, that clusters of galaxies contain far more mass than their visible light can account for, held up. It took nearly 4 decades for the idea to be taken seriously, and the person most responsible for that shift was astronomer Vera Rubin, working alongside instrument builder Kent Ford at the Carnegie Institution of Washington. In 1970, Rubin and Ford published rotation curve measurements of the Andromeda galaxy, tracking how fast stars and gas clouds orbited at different distances from Andromeda's center, using a highly sensitive spectrograph Ford had built himself. The expectation, based on ordinary Newtonian physics, and the same logic that governs how planets orbit the Sun, was that stars farther from the galactic center should orbit more slowly, the same way Neptune moves more slowly around the Sun than Mercury does. Instead, Rubin and Ford found the opposite. Stars near Andromeda's edge were orbiting just as fast as stars close to its center, producing what astronomers call a flat rotation curve instead of the declining Newtonian gravity predicted for visible matter alone. Through the 1970s and into the 1980s, Rubin, Ford, and collaborators including Norbert Thonard repeated the same measurement across dozens of other spiral galaxies, and every single one showed the identical pattern, flat rotation curves, meaning every one of those galaxies had to be embedded in some far larger, invisible halo of mass, extending well beyond its visible stars. By the early 1980s, thanks largely to this body of work, dark matter had moved from a decades-old oddity, dismissed by most of the field, into one of the central pillars of modern astrophysics. Rubin herself was famously cautious in how she described her own findings, often letting the data speak for itself rather than pushing a specific interpretation, and she consistently credited the work as a collaborative effort rather than claiming sole credit for the discovery. Today, astronomers estimate dark matter makes up somewhere around 85% of all the matter in the universe, with the ordinary visible material that makes up stars, planets, and people accounting for only a small remaining fraction, a genuinely strange fact to sit with, that nearly everything gravitationally holding galaxies and galaxy clusters together, including the scaffolding underneath the cosmic web itself, is made of something astronomers still can't directly see or fully explain, only infer from its gravity. Knots are the densest part of this web. Filaments are less dense, sheets are less dense still, and voids, the actual empty stretches between galaxies, have the lowest density of anything in the observable universe. That hierarchy matters, because it means the emptiness people imagine when they picture the space between galaxies isn't uniform at all. A stretch of space cutting through a filament still has meaningfully more material in it than a stretch cutting through a true void, and even the emptiest parts of intergalactic space still carry faint magnetic fields. Observations of high-energy light coming from distant blazars, which are galaxies with jets pointed directly at Earth, have set a lower bound on that magnetic field strength of at least 3 × 10⁻16th power in Gauss. It's a tiny number, but it means even the deepest void isn't a true physical zero. Something is still there, faintly, holding a trace of structure across all that distance. So what exactly is out there, physically, if you could stand in the middle of it? University of Colorado Boulder astronomer Michael Shull described it to Live Science this way. If you took a single cubic meter out of that space, there would be less than one atom inside it. That's the kind of emptiness that's genuinely hard to picture, since even the best vacuum chambers built on Earth still contain far more matter than that per cubic meter. And yet, when you add up all of that thin, scattered material across the entire volume of intergalactic space, it turns out to account for somewhere between 50 and 80% of all the ordinary matter in the universe. Read that again, because it's counterintuitive. The stuff floating in the gaps between galaxies outweighs, in raw total mass, the stuff sitting inside the galaxies themselves. Astronomers call this thin material the intergalactic medium, and it's mostly hot, ionized hydrogen, meaning hydrogen that's lost its electron, mixed with trace amounts of heavier elements like carbon, oxygen, and silicon. Nobody found this material by pointing a telescope directly at it, because it doesn't glow brightly enough to be seen that way. The actual discovery story is worth telling properly, because it starts with a very specific moment in 1963, when astronomer Martin Schmidt identified the first confirmed quasar, an object called 3C273, and quickly began finding others even farther away, pushing out to a quasar called 3C9 the following spring. Schmidt gave a talk about this discovery at Caltech, and in the audience sat a graduate student named Jim Gunn, who reportedly blurted out on the spot that this had to matter for cosmology. Within about a week, Gunn and a fellow graduate student, Bruce Peterson, had worked out why. If light from a quasar that far away had to travel through any meaningful amount of neutral hydrogen gas on its way to us, that gas would absorb a very specific, predictable slice of the quasar's light, a signature now called the Gunn-Peterson trough. Gunn and Peterson published their prediction in 1965, working through the physics with input from other physicists of the era, including John Bacall, Edwin Salpeter, and Dennis Sciama. It was a genuinely elegant idea, using the light of an extremely distant object as a kind of cosmic X-ray, revealing the invisible gas sitting between it and us purely by what it blocked out. The catch was that for more than 3 decades after that prediction, nobody had actually found a quasar distant enough to test it properly. That finally changed in 2001, when astronomer Robert Becker and colleagues, using the Sloan Digital Sky Survey, found a quasar at a redshift of 6.28 that showed exactly the absorption trough Gunn and Peterson had predicted 36 years earlier. It confirmed not just the presence of intergalactic gas, but gave astronomers a tool to date one of the most important transitions in the universe's early history, the period when that hydrogen gas shifted from mostly neutral to mostly ionized, called the era of reionization. In the decades since that first confirmed observation, astronomers have used this same basic trick, quasar light as a probe, again and again, and have mapped out vast webs and filaments of gas and heavy elements, together holding more mass than every galaxy in the universe combined, exactly the intergalactic medium described a moment ago. Now, before going further into the emptiness itself, it's worth pausing on how anyone even figured out this web-like structure existed at the larger, galaxy-scale level, because that story is its own piece of history, running in parallel to the quasar work, and it starts with a fairly simple idea, executed over a stretch of nearly 2 decades. The Center for Astrophysics in Cambridge, Massachusetts, began its first redshift survey back in 1977, with the straightforward goal of measuring how fast nearby bright galaxies were moving away from us. Redshift, for anyone unfamiliar with the term, is the stretching of light toward longer, redder wavelengths as its source moves away. And by measuring that stretch for a galaxy, astronomers can use Hubble's law to work out roughly how far away it is. Do that for enough galaxies, and you can start building an actual 3-dimensional map of a slice of the universe, rather than the flat, 2-dimensional picture a telescope naturally gives you. That first CFA survey wrapped up in 1982, and it already offered early evidence that galaxies weren't scattered randomly through space, that there was some kind of filamentary structure, and there were gaps where galaxies simply weren't present. Then, in the winter of 1984 into 1985, astronomers Margaret Geller and John Huchra kicked off a much larger second phase of the project, known as CFA2. Between 1985 and 1995, they and their students and collaborators measured redshifts for roughly 18,000 bright galaxies across the northern sky. And in 1989, while combing through that data, Geller and Huchra found something that genuinely surprised the field. A structure running across a huge stretch of sky, stretching somewhere in the range of 500 to 600 million light-years long, roughly 250 to 300 million light-years wide, and only about 15 to 30 million light-years thick, meaning it was shaped less like a clump and more like an enormous, thin sheet of galaxies stretched taut across a slice of the cosmos. They called it the Great Wall, and at the time, it was described in their published paper in the journal Science as possibly the largest single coherent structure yet detected in any redshift survey. What made it genuinely puzzling wasn't just its size. It was that a structure that large seemed almost too big to have formed through ordinary gravitational collapse in the time available since the beginning of the universe, which is part of why it caught the attention of astronomers well outside the immediate field. The Great Wall wasn't the final word, either. In 2003, astronomers working with data from the Sloan Digital Sky Survey, a far larger and more ambitious survey than the original CFA effort, identified an even bigger structure, one that came to be known as the Sloan Great Wall, stretching roughly 1.37 billion light-years across, more than twice the length of the original CFA Great Wall. The comparison matters because it illustrates something important about how this whole field works. Every time astronomers build a bigger, deeper survey, they tend to find bigger structures than the previous survey could have possibly detected, simply because the earlier survey wasn't looking far enough out to see the whole thing. The CFA Great Wall's size, in other words, was partly a limit of how far that particular survey could see, not necessarily the true edge of the structure itself. All of that mapping effort, stretching from the 1970s through the 2000s, is what eventually built up the picture described earlier, the cosmic web of knots, filaments, sheets, and voids. It didn't come from a single observation or a single insight. It came from decades of patient, repetitive measurement, redshift after redshift, plotted point by point, until the shape of the structure slowly emerged out of the data the way a photograph emerges out of a darkroom tray. There's one more piece of this mapping history worth including, because it directly explains why our own galaxy sits where it sits. In 2014, astronomer R. Brent Tully, working with an international team including Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, published a paper in the journal Nature that finally answered a question astronomers had been chasing since the 1970s and 80s, a mysterious pull tugging our galaxy and thousands of others toward a single point in space, a pull so strong it earned the nickname the Great Attractor. The trouble was that the Great Attractor sat in a direction largely obscured by the dust and stars of our own galactic plane, making it maddeningly difficult to study directly. Tully's team solved the puzzle not by looking directly at the Great Attractor, but by mapping the actual motion, the so-called peculiar velocities, of tens of thousands of galaxies across a huge stretch of the local universe, using radio telescope observations, including the National Science Foundation's Green Bank telescope. What emerged was a picture of an enormous gravitational basin, a region where all of the galactic flows inside it converge toward that same central point, the way streams across a landscape all eventually drain into the same valley. They named this entire basin Laniakea, a Hawaiian word chosen to mean immense heaven, honoring the tradition of Polynesian navigators who once used the night sky to cross the vastness of the Pacific Ocean. Laniakea spans roughly 500 million light-years across, contains an estimated 100,000 galaxies, and carries a combined mass of around 100 million billion suns. Tully himself later joked about how modest our own local naming conventions look by comparison, pointing out that we live in the local group, itself part of the local sheet, sitting right next to the local void, adding dryly that they wanted something a little more exciting than local for the supercluster as a whole. Our own Milky Way, it turns out, sits out on the outskirts of Laniakea, one gravitationally tugged galaxy among 100,000 others, all being pulled, slowly, toward the same distant valley in the cosmic landscape. That pull, though, turned out to be only half the story, and the other half is stranger. For decades, astronomers had measured our galaxy moving through space relative to the cosmic microwave background at a speed of around 1.4 million miles an hour, and the Great Attractor, later folded into the larger Laniakea picture, was the leading explanation for why. But in 2017, a team led by Yehuda Hoffman at the Hebrew University of Jerusalem, working alongside Brent Tully, Hélène Courtois, and Daniel Pomered, the same core group behind the Laniakea mapping, built an even more detailed three-dimensional map of galaxy motion, and found that the pull toward the Great Attractor and the larger Shapley concentration beyond it could only explain about half of our galaxy's actual speed. The rest, they found, was being driven from the opposite direction entirely, by an enormous, sparsely populated region of space, almost directly behind us, relative to the direction we're moving. A void, strictly speaking, can't literally push anything, since it has no mass to exert a force. But gravity is a competition between directions, and a region with unusually little matter in it exerts unusually little pull. So galaxies nearby drift away from that emptiness exactly as if something were shoving them from behind, simply because there's so much less pulling them back toward it than toward the crowded regions elsewhere. Hoffman's team named this newly identified underdensity the dipole repeller, and their published analysis, appearing in the journal Nature Astronomy, found that this push and the pull toward the Shapley concentration contribute in roughly equal measure to our galaxy's overall motion. As Hoffman put it at the time, it isn't just one dramatic attractor pulling us in a single direction, it's a genuine tug-of-war, pull from one side and push from the other, and our galaxy's actual path through space is the net result of both forces working at once. It's a small, elegant piece of the puzzle, but it reinforces something that keeps surfacing throughout this whole topic. That emptiness in the universe isn't a passive backdrop. It has its own kind of gravity, or rather its own kind of missing gravity. and that absence is just as capable of steering a galaxy's motion across hundreds of millions of light-years as any crowded, star-filled region ever could. With that history in mind, go back to the voids themselves, because they deserve a much closer look than a passing mention. These aren't small gaps. A typical void runs somewhere between 10 and 100 megaparsecs across, which works out to roughly 30 to 300 million light-years in diameter, and the truly massive ones, the ones astronomers call supervoids, are defined by an almost complete absence of the rich superclusters that usually anchor the cosmic web. Altogether, these voids are estimated to take up about 80% of the volume of the entire universe, while holding only about 10% of its mass. So by pure volume, emptiness is the default state of the cosmos, and galaxies, with all their stars and light and noise, are actually the exception, clustered into a small fraction of the available space. One void in particular has become the textbook example, mostly because of how strange its discovery was. In 1981, astronomer Robert Kirshner was running a redshift survey of his own, much like the CFA team, when he came across a patch of sky in the direction of the constellation Boötis that had almost nothing in it. Where he expected to find roughly 100 galaxies in that patch, he found 3. Follow-up surveys through the 1980s confirmed it wasn't a fluke, and the region became known as the Boötis Void, nicknamed, only half-jokingly, the Great Nothing. Estimates of its exact size vary a bit depending on which survey you check, but the commonly cited figure puts it at roughly 330 million light-years across, with its center sitting around 700 million light-years from Earth. Inside that entire volume, astronomers have only ever found about 60 galaxies, compared to the roughly 2,000 you'd expect to see in a region of ordinary cosmic density that size. It is not, technically, completely empty. There are those 60 galaxies scattered through it, and there's a thin structure of intergalactic gas as well. But relative to everywhere else that's been mapped, it might as well be a hole cut into the fabric of the universe. Here's where it gets stranger still, because those 60-odd galaxies scattered inside the Boötis void, and the galaxies found inside other voids like it, aren't just ordinary galaxies that happen to end up in an empty neighborhood. Astronomers have specifically studied what are called void galaxies, meaning galaxies confirmed to sit in these deep, underdense regions, and compared them to similar galaxies living in normal, crowded parts of the universe. What they've found is that void galaxies tend to behave differently. Multiple studies using data from the Sloan Digital Sky Survey, examining galaxy samples running well over 100,000 objects at a time, have found that void galaxies tend to have higher specific star formation rates than similarly sized galaxies living in denser regions, meaning they're forming new stars faster relative to their existing mass. They also tend to be bluer in color, which in astronomy usually signals younger, hotter, more recently formed stars, and they tend to hold onto larger, less disturbed reservoirs of gas, the raw material stars are made from. One survey summarized it by saying, void galaxies appear to reside in what amounts to a more youthful state of star formation compared to their counterparts elsewhere. The likely explanation comes down to something almost mundane once you say it out loud. Galaxies in crowded regions get bumped around constantly. They pass close to neighbors, get stripped of gas by tidal forces, get their star-forming material yanked away or disrupted by nearby companions. Galaxies sitting alone in the middle of a 300 million light-year void experience, essentially none of that. They're left to quietly evolve on their own, undisturbed, holding onto their gas and continuing to form stars at their own pace, without interference from neighbors that, in a void, mostly don't exist. Some researchers have gone further, using these isolated dwarf void galaxies to study what a nearly undisturbed pocket of the universe looks like, since they may offer a window into more primordial conditions, largely free from the environmental effects, tidal stripping, and gas starvation that reshape galaxies in busier neighborhoods. It's a genuinely strange thought. The very same emptiness that would be so hostile and disorienting to a person or a stray star turns out to be a kind of shelter for the handful of galaxies lucky enough to end up floating in it. Closer to home is a smaller, more personal version of this same story, the local void, the underdense region bordering the flat arrangement of galaxies that includes our own Milky Way, an arrangement astronomers call the local sheet. The local void extends roughly 60 megaparsecs, or about 200 million light-years, starting right at the edge of our own local group of galaxies, and its center is estimated to sit at least 23 megaparsecs, or about 75 million light-years, from Earth. Brent Tully, the same astronomer behind the Laniakea mapping project, has separately argued there's compelling evidence that matter is actively being pushed away from the local void at high velocity, which would mean the void isn't just sitting there passively empty, it's expanding, evacuating whatever little matter drifted into it in the first place. We are, in a very real sense, living right next door to one of these enormous nothings, close enough that its gravity, or rather its lack of gravity, is measurably nudging our own galactic neighborhood. And the Boötes void isn't even the largest one known. The giant void in Canes Venatici, discovered in 1988, measures somewhere between 1 and 1.3 billion light-years across, which makes it the second largest known void and puts emptiness itself on a truly cosmic scale. So that's the physical setting: the web, the voids, the galaxies quietly living inside the emptiness, and the decades of survey work that revealed all of it. Now here's where it gets stranger in a more personal way, because that same emptiness isn't just hosting gas and magnetic fields and structure, it's hosting stars. Actual stars, the same kind that make up constellations, except these ones aren't attached to any galaxy at all. The theoretical idea came first, decades before anyone actually found one. Back in 1988, astrophysicist Jack Hills, working at Los Alamos, proposed that these stars should exist as a natural consequence of a supermassive black hole sitting at a galaxy's core. His math worked like this. If a tightly bound pair of stars wanders close enough to a black hole that's powerful, the black hole's gravity can rip the pair apart, capturing one star permanently while flinging the other outward with tremendous force, potentially fast enough, in his calculations, to reach speeds up to 4,000 kilometers per second. For years, this stayed a theoretical prediction, a plausible piece of math without a confirmed real-world example. Then, in 2005, astronomer Warren Brown, working at the Smithsonian, found the first one. While surveying a class of stars called blue horizontal branch stars, Brown stumbled across an object catalogued as SDSS J090745.0 plus 024507, sitting out in the constellation Hydra, moving at a velocity that made no sense for an ordinary star. It was the first confirmed hypervelocity star, unbound to the galaxy, moving fast enough to eventually leave it entirely. Brown didn't stop there. Over the following years, he became, by his own account, a dedicated hypervelocity star hunter, and by the time Hubble imaging campaigns were being used to nail down these stars' exact trajectories, Brown had personally discovered 14 of the 16 known hypervelocity stars confirmed at that point. One of the strangest individual cases Brown's team studied is a star called HE0437-5439, first picked up in 2005 using the Very Large Telescope's Quayan instrument in Chile, sitting in the direction of the constellation Dorado, roughly 200,000 light-years out. This star is moving at around 1.6 million miles an hour, close to 3 times the orbital speed of our own Sun around the galactic center, and it presented astronomers with a genuine puzzle. The star's mass, about 9 times that of the Sun, and its blue color meant it should have burned through its nuclear fuel in only about 20 million years. But its speed and position meant it would have needed roughly 100 million years to travel from the Milky Way's core out to where it currently sits, a timeline that simply didn't match the star's expected lifespan. Something didn't add up, and the explanation Hubble Space Telescope researchers eventually settled on is almost cinematic in scope. Roughly 100 million years ago, a triple star system passed too close to the black hole at our galaxy's center. The black hole captured one of the 3 stars permanently, while flinging the other 2 outward together. Those 2 surviving stars, still gravitationally bound to each other as they were hurled outward, eventually merged into a single, hotter, more massive star, essentially resetting its internal nuclear clock in the process, which is why it still looks young today, despite the long journey. Warren Brown, commenting on the case, put it plainly: the star is traveling at what he called an absurd velocity, roughly twice what it would need just to escape the galaxy's gravity. And there's no ordinary process that produces a star moving that fast. Something exotic has to be behind it. HE0437-5439 is currently rocketing through the Milky Way's distant outskirts, on a trajectory that will eventually carry it into true intergalactic space, joining the population of homeless stars this video keeps circling back to. Then there's US 708, a star with an entirely different origin story, one that doesn't involve the central black hole at all. First spotted as a faint blue object all the way back in 1982 by Peter Usher and colleagues at Pennsylvania State University, it was essentially forgotten until the Sloan Digital Sky Survey rediscovered it in 2005. A decade later, in 2015, a team led by Stefan Geyer at the European Southern Observatory published findings in the journal Science, establishing that US 708 was moving at roughly 1,200 kilometers per second, about 2.7 million miles an hour, making it, at the time, the fastest star ever measured in the Milky Way. What sets US 708 apart isn't only the speed, it's the mechanism. This star used to be a normal red giant, locked in a binary system, gradually having its outer hydrogen layers stripped away by a hungry white dwarf companion orbiting nearby, until that companion accumulated enough stolen material to trigger a specific, statistically rare kind of stellar explosion called a Type E supernova. That explosion is what launched US 708 onto its current, blistering trajectory. Not a black hole encounter, but a supernova detonation in a binary system, a completely separate mechanism for creating a hypervelocity star. Stefan Geyer noted plainly that US 708 does not come from the galactic center, since there's no known second supermassive black hole in our galaxy capable of producing that kind of kick, and a smaller stellar mass black hole simply isn't strong enough to do the job. US 708 is now a rapidly rotating, helium-rich remnant, essentially a stripped stellar corpse, moving fast enough to escape the galaxy entirely, and researchers estimate it will actually leave the Milky Way in about 25 million years, eventually cooling into a lone white dwarf, drifting through the same intergalactic emptiness already discussed. Between these individual well-documented cases and the broader population studies, the Vanderbilt research from 2012 remains the anchor for understanding this phenomenon at scale. Astronomers Kelly Holly Bockelman and graduate student Lauren Palladino, publishing in the Astronomical Journal, identified more than 675 stars sitting on the outskirts of the Milky Way, out in the intergalactic space between our galaxy and Andromeda. They argued these stars had been ejected from the galactic core itself, and what gave them away was their color. As Holly Bockelman put it, these stars really stand out because they're red giant stars with high metallicity, meaning they contain more heavy elements than you'd expect this far out, and that gives them an unusual color that doesn't match the older, metal-poor stars normally found drifting at the edges of a galaxy. The stars in that sample would have started out as small, ordinary stars, similar to our own Sun, before a black hole encounter sent them hurtling outward, aging into red giants along the way as they traveled. Even moving at hypervelocity, a star needs roughly 10 million years just to cross from the galaxy's central hub out to the edge of the spiral, a distance of about 50,000 light-years. As Holly Bockelman summarized it, studying these rogue stars offers a way to learn about the history and evolution of our own galaxy, essentially using the wreckage flung outward from violent events at the core to reconstruct what happened there in the first place. At the time of that study, only 16 hypervelocity stars had been confirmed while still inside the Milky Way, meaning the 675 candidates found already out in intergalactic space represented a huge jump in the known population, stars that had already made the full outward journey and were now sitting in the gap toward Andromeda. Then, in 2018, a separate study, published in monthly notices of the Royal Astronomical Society, made the picture stranger still. Researchers examined 20 hypervelocity stars and tried to trace each one back to its point of origin. 7 of them lined up with an origin inside the Milky Way's own galactic disk, exactly what you'd expect from the black hole ejection mechanism. But the other 13, including the 2 fastest of the entire group, moving at around 1.5 million miles an hour, couldn't be traced back to the Milky Way at all. The implication is that these 13 stars may have originated in another galaxy entirely, meaning the Milky Way isn't just a place that ejects rogue stars outward into the dark. It might also be a destination, quietly receiving stray stars that were flung out of some other galaxy long ago, and have simply been drifting through intergalactic space ever since, passing through our neighborhood the way a stranger passes through a town on their way somewhere else. There's also a smaller scale version of this happening right in our own galactic backyard. The Large Magellanic Cloud, our nearest large satellite galaxy, is now understood to host its own supermassive black hole, estimated at somewhere in the neighborhood of 600,000 times the mass of the Sun, confirmed through evidence announced by the Center for Astrophysics in March of 2026. Around 21 hypervelocity stars found within the Milky Way's halo are now thought to have been ejected not from our own galactic center at all, but from the Large Magellanic Cloud kicked outward through that same Hill's mechanism, just operating on a smaller satellite galaxy instead of the Milky Way itself. So the process isn't unique to major spiral galaxies. It appears to happen anywhere a sufficiently large black hole and a close binary star pair happen to cross paths, which, across billions of years and billions of galaxies, turns out to be often enough to populate the gaps between galaxies with a genuinely large, scattered population. And this isn't a rare, isolated phenomenon limited to our own galactic neighborhood in a broader sense either. Out in the Virgo cluster, a massive collection of roughly 2,500 galaxies, astronomers estimate that intergalactic stars, stars untethered to any single galaxy, make up around 10% of the cluster's total mass. That's potentially enough mass to outweigh any single one of those 2,500 galaxies individually. Picture that for a second. An entire population of homeless stars, drifting in the gaps between galaxies, collectively weighing more than any one full galaxy in the cluster they're scattered through. Which brings up the obvious question: what would it actually look like and feel like to be one of those stars, or to be standing on a hypothetical planet orbiting one? What would the sky show you? Based on everything covered so far, the honest answer is almost nothing. No glowing band of a galaxy overhead, because you'd be sitting outside of one. No dense scattering of nearby stars, because the average distance between stars even within a crowded galaxy is already around 100 billion miles. And out in true intergalactic space, that spacing would only be more extreme, since you're specifically in the gap between galactic structures rather than within one. The sky wouldn't be a rich field of stars. It would be dominated by darkness, with a scatter of extremely distant, extremely faint smudges of light, representing entire galaxies seen from far outside, rather than the close, bright pinpricks we're used to from inside our own. This is where the calm horror in the title actually comes from, and it's worth being precise about what that means, because it isn't the horror of danger. A rogue star or a hypothetical world drifting in intergalactic space isn't threatened by monsters or catastrophe. It's something quieter and, honestly, harder to sit with. Distance without end, silence without interruption, isolation that isn't a temporary condition, but the literal permanent structure of the place you're in. There's no rescue coming from a neighboring system, because there is no neighboring system, not for millions of light years in any direction. It's less like being lost at sea, and more like being the only object in an ocean so large that the concept of a shore stops applying at all. Now bring this back closer to home, because our own galaxy is not exempt from this story. It's a future participant in it, and it comes with a full cast of characters worth introducing properly, because most people have heard of Andromeda, but have no idea how many neighbors we actually share this stretch of space with. Our galactic neighborhood, called the Local Group, spans roughly 10 million light-years across, and contains something like 50 confirmed galaxies, with surveys suggesting the true number, once every faint, ultra-dim dwarf galaxy is accounted for, could run well past 100. Most of them are small. 3 galaxies dominate the group by size: the Milky Way, Andromeda, and the somewhat smaller Triangulum galaxy, also known as M33, sitting roughly 3 million light-years away, and considered the third largest member of the group, likely itself a satellite loosely bound to Andromeda's gravity. Everything else, dozens of dwarf galaxies with names like the Sagittarius dwarf, the Fornax dwarf, the Sculptor dwarf, and a long list of ultra-faint dwarf spheroidals, orbits one of these 3 larger galaxies like moons around a planet, or drifts more loosely through what astronomers call the Local Group Cloud. 2 of the Milky Way's own satellite galaxies happen to be visible to the naked eye from the southern hemisphere, the Large and Small Magellanic Clouds. named after Ferdinand Magellan, whose voyage brought them into common Western knowledge in the 16th century, though there's a written mention of them dating back even earlier, to a 1502 letter by the explorer Amerigo Vespucci. The Large Magellanic Cloud sits roughly 160,000 light-years away and is considered the fourth largest galaxy in the entire local group, holding an estimated 1/100th the mass of the Milky Way, rich in gas and currently undergoing vigorous star formation. The small Magellanic Cloud sits a bit farther out, and the two are connected by a bridge of hydrogen gas, evidence that they've been gravitationally tangled up with each other for a very long time. Interestingly, measurements taken with the Hubble Space Telescope and announced in 2006 suggest both Magellanic Clouds may actually be moving too fast to be permanent, long-term companions of the Milky Way at all. If they are in a bound orbit, it would take at least 4 billion years to complete just one loop, and it's possible we're witnessing their first close approach, meaning what looks like a stable, ancient relationship might actually be the opening act of a merger that could unfold on a similar timescale to our own coming collision with Andromeda. None of this is static either. The Milky Way is currently in the process of shredding and slowly absorbing the Sagittarius dwarf spheroidal galaxy, pulling its stars apart into long streams that wrap around our own galaxy, and astronomers expect the Milky Way will eventually absorb both Magellanic Clouds as well, long before Andromeda ever arrives. Meanwhile, over on Andromeda's side of the local group, evidence of similar past meals is written right into its structure. The remains of dwarf galaxies that Andromeda has already consumed can still be traced in its outer halo, and Andromeda carries its own family of smaller companions, including the compact elliptical M32 and the dwarf elliptical NGC 205, both of which sit close enough to Andromeda that they show up in the same telescope frame practically every time astronomers point one in that direction. In other words, before the two giants of our local group ever collide with each other, they're each already quietly eating their own smaller neighbors, one dwarf galaxy at a time, in a slow, ongoing process that's been running for billions of years and will keep running, regardless of what eventually happens between the Milky Way and Andromeda themselves. Which brings us to that main event. Right now, the Andromeda galaxy sits about 2.5 million light-years away from us, and it happens to be the single most distant object visible to the naked eye from Earth. It's also approaching us, closing that gap at a speed estimated somewhere in the range of 250,000 to 400,000 kilometers per hour, depending on which measurement you check. In 2012, a team working with the Hubble Space Telescope, using proper motion measurements built from a full decade of accumulated imaging data going back to 2002, announced they could say with confidence that a head-on collision between the Milky Way and Andromeda was essentially locked in, expected to begin in about 4 billion years, with the full merger into a single galaxy, nicknamed Milkomeda, completing roughly 2 billion years after that first collision, putting the total timeline at around 6 billion years from now. Here's where the story gets appropriately messier, because science doesn't stay still, and this is a good example of that. In 2025, physicist Till Sawala and a team of colleagues revisited the whole calculation using much newer data from the Gaia spacecraft and Hubble, data that simply wasn't available back in 2012. They ran 100,000 separate simulations across 22 different variables that could affect the outcome, and the results shifted the odds noticeably. Looking only at the Milky Way and Andromeda in isolation, they found roughly a 50% chance of collision within the next 10 billion years, which already softens the 2012 near certainty. But once they factored in the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, two smaller neighbors whose pull subtly changes the trajectories involved, the odds of a genuine head-on collision within the 4 to 5 billion year window dropped all the way down to about 2%. In roughly half of their simulated outcomes, the two galaxies don't collide head-on at all. They instead swing past each other at a distance of around 500,000 light-years, and only gradually spiral together afterward through a slow process called dynamical friction, which could stretch the eventual merger out over a far longer and less dramatic timeline. In the scenarios where a merger does eventually happen, Triangulum tends to show up as a third participant, typically ending up orbiting the merged remnant and folding into it roughly 6 billion years from now, potentially preserving a bit of spiral structure in the final combined galaxy rather than the fully smooth elliptical shape earlier models predicted. So the honest current answer to whether Andromeda and the Milky Way will definitely collide is that it's genuinely an open question, actively being revised as better data comes in, and the sensible thing to do is present both the 2012 near certainty and the 2025 reassessment rather than pretending either one has the final word. Whichever version turns out to be closer to reality, the numbers involved in the galaxies themselves are worth sitting with. Andromeda is estimated to contain around 1 trillion stars. The Milky Way holds roughly 300 billion. And despite two galaxies of that size potentially plowing directly through each other, the actual odds of even two individual stars colliding are considered vanishingly small because of how much empty space separates stars even within a single galaxy. The average distance between stars is roughly 100 billion miles, which one common comparison describes as being like placing a single ping-pong ball every 2 miles. If the Sun were shrunk down to the size of that ping-pong ball, the nearest star to us, Proxima Centauri, 4.2 light-years away, would be a P sitting roughly 680 miles off. Multiply that spacing across two galaxies with over 1 trillion stars combined, and you start to understand why astronomers describe galactic collisions less like a car crash and more like two clouds of smoke drifting through one another, mostly passing straight through with barely a disturbance at the level of individual stars. But not entirely without disturbance. Some stars, caught at the wrong place during that gravitational chaos, will get flung outward, ejected the same way US 708, HE 0437-5439, and the Vanderbilt team's 675 candidates were ejected from the Milky Way's core or from a supernova detonation in a binary pair. In other words, whatever eventually happens between the Milky Way and Andromeda, a fresh population of rogue, homeless stars is a near-certain byproduct. More stars added to that same category, already drifting out there right now, waiting between galaxies. And at the very center of it all, the supermassive black holes anchoring each galaxy will eventually spiral into one another and merge, a process on its own that could take millions of years to complete. It's worth pausing on one more detail here, because it's easy to lose in all the deep time and big numbers. Long before any of this galactic drama plays out, Earth's own oceans are expected to boil away due to the Sun's gradually increasing luminosity, on a timeline estimated somewhere between 500 million and 1.5 billion years from now, meaning any human witness to the actual galactic merger is, at best, a thought experiment used by scientists to make the scale of the event feel tangible, not a literal expectation. The point of these vivid descriptions in the astronomy literature, the sky filling horizon to horizon with Andromeda's stretched-out light, isn't meant as a prediction that anyone will see it. It's a way of making an otherwise abstract number, 4 billion years, feel like something a person could actually stand underneath. Before jumping to the far future, it's worth explaining exactly why anyone believes the universe's expansion is speeding up in the first place, since that single discovery is what makes everything past this point in the video true. In the 1990s, two independent groups of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt, with Adam Rees leading the data analysis, were both using a specific kind of stellar explosion called a Type 1a supernova, as what astronomers call a standard candle. Because these particular supernovae explode with a remarkably consistent peak brightness, comparing how bright one actually is to how bright it appears from Earth lets astronomers calculate its distance with real precision, and comparing distances at different points in cosmic history lets them reconstruct how fast the universe has been expanding at each stage. Both teams set out expecting to measure how much the expansion was slowing down over time, since gravity, pulling everything in the universe back together, should have been acting as a natural brake on the expansion that began at the Big Bang. Instead, in 1998, both teams independently found the opposite. Distant supernovae were dimmer and therefore farther away than a slowing, decelerating universe could explain. The only way to account for it was if the expansion itself was accelerating, being pushed apart faster over time rather than gradually easing off. The discovery implied the existence of some kind of repulsive force spread evenly throughout space, a force that came to be called dark energy. and it was named the journal Science's Breakthrough of the Year for 1998. In 2011, Perlmutter, Schmidt, and Rees were jointly awarded the Nobel Prize in Physics for the discovery. More than a decade of further research has confirmed the acceleration is real, even as the underlying question of exactly what dark energy actually is remains honestly unresolved. It's worth being direct about that. Astronomers are confident the acceleration exists and can measure it precisely, but nobody has yet identified what physical mechanism is causing it. That admission of uncertainty isn't a weakness in the science. It's simply where the evidence currently stops, and it's the same accelerating expansion, confirmed by that 1998 discovery, that drives everything discussed in the rest of this video. Before going further, it's worth explaining exactly what that second pillar of evidence, the cosmic microwave background, actually is, since the discovery story behind it is one of the stranger accidents in the history of science, and makes the later argument land harder. Back in 1964, two radio astronomers at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna, originally built for early satellite communication, to study radio emissions from our own galaxy. No matter what they did, they kept picking up a faint, steady hiss of background noise, coming from every direction in the sky, at every time of day, in every season. They assumed it had to be some flaw in their equipment. They checked the wiring. They pointed the antenna at New York City to rule out human interference. They even discovered a pair of pigeons nesting inside the antenna and evicted them, scraping out the accumulated droppings, thinking that might be the culprit. The noise never went away. Eventually, after more than a year of troubleshooting, Penzias and Wilson learned that a group of physicists at Princeton, led by Robert Dick, had independently predicted that if the universe really did begin in a hot, dense Big Bang, it should have left behind a faint bath of leftover radiation, cooled by billions of years of cosmic expansion, down to just a few degrees above absolute zero, uniformly filling the entire sky. Penzias and Wilson's stubborn, accidental noise turned out to be exactly that radiation, the cosmic microwave background, the actual afterglow of the Big Bang itself, still detectable nearly 14 billion years later. The discovery was published in 1965, and it became one of the central pillars of evidence for the Big Bang model, earning Penzias and Wilson the Nobel Prize in Physics in 1978. It's worth sitting with the accidental nature of that discovery for a second, a persistent hum that two scientists spent over a year trying to explain away, before instead realizing they'd stumbled onto direct evidence of the origin of everything. That's the exact signal Krauss and Scherer argue will eventually stretch and dilute past the point of detection in the far future. The same faint noise that once seemed like nothing more than pigeon droppings and faulty wiring, quietly carrying proof of the universe's beginning across the entire sky for as long as any future civilization remains able to detect it. Now stretch the timeline out even further, past every human civilization, past the collision, past the merger, into territory that starts to feel less like astronomy and more like philosophy dressed up in physics. In 2007, physicists Lawrence Krauss and Robert Scherer published a paper with a blunt title, The Return of a Static Universe and the End of Cosmology. Their argument goes like this. The universe's expansion isn't just continuing, it's accelerating, driven by that same dark energy just described. And because of that acceleration, every galaxy outside our own local group will eventually cross what's called a cosmological event horizon, a boundary beyond which their light can genuinely never reach us again, no matter how long we wait. Krauss and Scherer argue this process will erase, one after another, the three main pillars of evidence that currently tell us the universe began in a Big Bang. First, the redshift of distant galaxies, the observation that everything is rushing apart, will lose its meaning once there's nothing left out there to measure that motion against. Second, the cosmic microwave background, the faint leftover glow from the early universe, will get stretched and diluted so far that no future instrument could ever detect it. Third, the precise ratio of light elements like hydrogen and helium left over from the universe's first few minutes will get buried under the output of countless later generations of stars processing and reprocessing that material. Their conclusion is genuinely striking. A hypothetical future astronomer doing careful, honest, rigorous science with everything still visible to them at that point in cosmic history, could reasonably look at the sky and conclude they live in a single, static, eternal galaxy, with absolutely no evidence that a Big Bang ever happened, unless some record from an earlier, better-informed era happened to survive and get passed down. This isn't meant to happen quickly on any human timescale. Under current models, the most dramatic disappearance of visible galaxies plays out over roughly the next 100 billion years, and the process is considered basically complete, decisively, over trillions of years. It's also worth being honest that this entire scenario rests on an assumption, specifically, that dark energy keeps behaving the way it currently appears to behave, as a steady, unchanging cosmological constant. If that assumption turns out to be wrong, if dark energy weakens, strengthens, or changes character over time, the whole timeline shifts, potentially dramatically, and the far future could look very different from what this model predicts. So this is best understood as a serious, well-reasoned extrapolation from current physics, not a locked-in certainty. What does remain, according to this picture, is our own local group, the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and their smaller satellite galaxies, all gravitationally bound tightly enough to one another to resist being pulled apart by the universe's overall expansion. Everything else, every galaxy that isn't already gravitationally attached to us, eventually drifts beyond the reach of any future telescope, any future civilization, any future observation at all. The local group itself will merge into one single galaxy, sitting essentially alone in a black and, from any internal vantage point, endless void, cut off not by distance in the ordinary sense, but by the expansion of space itself, outrunning the speed of light between us and everything else. This raises a strange, almost practical question that some physicists have taken seriously enough to write about directly. What happens to any advanced civilization that's still around once every other galaxy has slipped past that horizon? Physicist Freeman Dyson considered a related energy problem back in 1960, decades before anyone was discussing accelerating expansion at all, when he proposed, in a short paper in the journal Science, that any sufficiently advanced civilization would eventually need to capture the entire energy output of its home star just to keep growing, an idea he was partly inspired by a 1937 science fiction novel called Star Maker by Olaf Stapledon, which described alien civilizations wrapping entire stars in structures to harvest their light. Dyson's concept, now generally called a Dyson sphere or Dyson swarm, involves surrounding a star with a vast number of orbiting collectors, absorbing its visible light and re-radiating the leftover heat as infrared radiation, something Dyson suggested could theoretically be detected from other star systems as a signature of an advanced civilization at work. In the decades since, researchers speculating on the far future have connected Dyson's original idea to the exact isolation problem Krauss and Scherer described. If a civilization is eventually confined to just its own local group, with every other galaxy in the universe permanently out of reach, one proposed survival strategy is exactly this kind of large-scale energy harvesting, wrapping stars in collectors to squeeze every possible unit of usable energy out of the limited number of stars still gravitationally available, before the accelerating universe puts everything else permanently out of reach. It remains, worth stressing, entirely speculative physics commentary, rather than a settled prediction, but it's a genuinely useful way of making the abstract idea of cosmic isolation feel concrete. An entire civilization, however advanced, ultimately boxed in by nothing more dramatic than the ordinary stretching of space, forced to live within whatever handful of galaxies happened to be gravitationally glued together before the rest of the universe drifted out of reach forever. Before getting to what all of this actually means, though, it's worth bringing the story all the way up to the present, because this isn't just a settled historical topic. Astronomers are actively refining this picture right now, with tools that didn't exist even a few years ago. The James Webb Space Telescope, since coming online, has been used to push the study of the cosmic web back further in cosmic time than ever before. In a program called ASPIRE, led by Feige Wang of the University of Arizona, astronomers using Webb spotted 10 galaxies aligned in a thin thread, roughly 3 million light-years long, anchored by a distant, extremely early quasar, one of the earliest filamentary structures ever associated with such a quasar, dating to a period not long after the universe's so-called Dark Ages ended. And more recently, an international team led by researchers at the University of California, Riverside, used Webb data to build what's been described as the most detailed map of the cosmic web ever assembled, tracing nearly 800,000 galaxies across almost the entire history of the observable universe, all the way back to when the cosmos was less than 1 billion years old. Laid out visually, the map shows exactly the pattern this whole video has been describing: bright, dense clusters and filaments threading through vast, darker, nearly empty voids, except now stretching across nearly 14 billion years of cosmic history in a single coherent picture. It's a nice reminder that everything covered in this video, the web, the voids, the rogue stars, the coming collision, the far future, isn't some closed chapter of textbook astronomy. It's an active, ongoing area of research, being redrawn and refined practically every year, as bigger telescopes and bigger surveys keep finding more of the structure and more of the emptiness than the previous generation of instruments ever could. Sit with that for a second, because it reframes everything discussed earlier in this video. The rogue stars drifting between the Milky Way and Andromeda right now, homeless, isolated, kicked out of their galaxy of origin by a black hole encounter or a supernova detonation, are a small-scale preview of a fate the entire universe seems to be heading toward on a much larger scale. Not violent destruction, not an ending in the dramatic sense most people picture when they think about the fate of the cosmos, but a slow, physically inevitable drift toward total isolation, structure withdrawing into itself, galaxies retreating past the horizon one by one until whatever remains is simply alone, with no observable evidence left behind of everything that came before it. That's the actual, verified shape of the story. Space between galaxies isn't a true void in the way people picture it. It's a thin, structured medium carrying more mass in total than the galaxies themselves, first revealed indirectly through a 1965 prediction about quasar light that took 36 years to confirm, and mapped out on a larger scale through decades of patient redshift surveys, from the CFA project's first slice of the universe in the late 1970s, through the discovery of the Great Wall in 1989, the even larger Sloan Great Wall in 2003, and finally, the 2014 mapping of Laniakea itself, the enormous gravitational basin our own galaxy quietly sits inside. That same structure is bordered by genuine cosmic voids, some stretching past 1 billion light-years across, quietly hosting their own small, undisturbed, oddly youthful galaxies that seem to thrive precisely because nothing else is around to bother them. Real stars, hundreds of them at minimum, sit out in the gap right now between our galaxy and Andromeda, some ejected by violent encounters with the black hole at our galactic core, others, like US 708, blasted loose by a supernova in a stripped-down binary system, and others still, like the 13 stars from the 2018 study, may not even be ours to claim, having arrived here from somewhere else entirely. Our own galaxy sits inside a crowded, tangled neighborhood of dozens of smaller companions, several of which it's already quietly consuming, and it's on a collision course with Andromeda that current science treats as somewhere between a near certainty and a coin flip, depending on which measurement generation you trust. An encounter that, either way, is expected to mint a fresh batch of the same kind of homeless, rogue stars already drifting out there. And past all of that, past a 1998 discovery that earned a Nobel Prize, past every human timescale and every galactic merger, the honest physics points toward a universe that keeps expanding away from itself, until, eventually, isolation isn't just something that happens to a handful of unlucky stars kicked loose from a supermassive black hole. It's the final, quiet state of everything, and perhaps, if Dyson's old idea about capturing a star's full energy output ever gets put to real use, the final, quiet state that some distant civilization simply learns to live inside. If any part of that stuck with you, the way it did with me while putting this together, let me know in the comments which detail hit hardest, whether it was the rogue stars, the discovery of the Great Wall, the strangely undisturbed void galaxies, the mapping of Laniakea, or that slow fade toward cosmic isolation billions of years from now. Thanks for watching all the way through, and I'll see you in the next one.